Here we go. What was the table that you guys were writing down in your notes at the beginning of class? Well, so what's legal to do with vectors? Basically, adding, subtracting, distributing, multiplying. Have some ones and some zeros in there. You have some ones and some zeros in there. As far as identities, 1 times vector u is still itself. 0 times vector u is still 0. Where's the one property that has a magnitude in it? Which one? Yeah, number 9. Number 9 has a magnitude in it because remember the number 9 has magnitudes in it. You have a lot of different operations going on, but there's one thing that's specifically missing. Can anybody figure out the one operation that's missing? And it's missing for a very important reason because it has its own special way of doing it that we won't even talk about until the next section. What's one operation that's missing? You could say division or subtraction, but technically, couldn't we have a vector that's a negative? So couldn't you add a negative vector and it'd be okay? And there's technically a negative right there, negative subtracting. Some of you guys said dividing, but couldn't I have a constant that's 1 over that's kind of like dividing? Couldn't you have like u over 2 and it'd be like 1/2 times u? Division could be multiplying. So actually division is in here by a constant and subtraction is in here. But what's not in here? Look at the u's and look at the v's and look at what is not ever true in any of these properties. U is being added to v, u can be subtracted from v, but they can never be? Well, no, we have u and u. I guess it could be u and u, is u and u. A little bit louder, Kyle, what? What's never true? But there are 0 vectors. U actually can be equal to 0.
U and v can never be equal?
I guess they could be, though, couldn't they? But you're right, it's not a property on here. U equals v is not a property on here. It's because it usually doesn't happen. Usually they're different sizes. So it's not really a property that u equals v. Think about operations. U and v don't get multiplied. Check it. Are there any u's next to v's? There are constants multiplied. There are constants multiplied, but the u's and v's are always what? Like if they're present, what are they always doing? They're always adding, which could also be subtracting. They're always adding, or I guess you could also say subtracting, but they're never multiplying or dividing. U times v and u over v is not anywhere in this chart. So even though a lot of these are super common sense, do you guys realize that when you were writing it? Super common sense. Like, oh, distribute the u, no big deal. Yeah, you're right, distribute the u. Or, hey, we can distribute the c. Yeah, you're right. Hey, we can reorder the parentheses a little bit and multiply in different orders. Yeah, you're right, as long as they're constants. So a lot of things are like, oh, basic, easy, cheesy, got it, no big deal. But if I was to say something like uv equals vu, what would most of you have said before I just stated what I stated? uv equals vu, you'd be like, yeah, of course, duh, and it's totally wrong. Because u times v acts in a completely different way than adding and subtracting. So some things are super basic, some things are super straightforward. Vector addition and subtraction, and scalar multiplication and division. Super straightforward, super basic in the sense of following the math properties that you've been learning for a long time. But what's not on there is vector multiplication. Ugh. That's a whole other beast for a whole other section. Okay, unit vectors. I need you guys to grab out a highlighting pen or a highlighter itself, something of a color that will make it jump out to you, because this page is the one that kids tend to ignore, avoid, and then get wrong. Or not be ready for in the homework. Oh, you guys left me one. No one wanted to eat the last one, huh? I got you. If I were you, I would highlight unit vectors because Nope. There we go. When you get to it in homework, when you get to it in the test review, when you get to it on the test, if you haven't studied it, very few of you would naturally get it. This is a page, if you haven't studied, very few of you would naturally get. So you guys should have written little arrows above your V's. And I also said, but you might not have caught it, above your I's and J's. Now some people, including me, instead of putting a dot and a vector arrow, just put a vector arrow instead of a dot. Totally fine. You don't have to do that, but totally fine. You could do it instead of the point, or you could have it go through, or you could have it go above. It doesn't really matter. But vectors, or I's and J's, are vectors. Let me show you a little basic I down here. I put little tails forward on my I's just because that way, I don't know, you know it's not a 1. I is going to be this little guy down here. Struggle. I'm trying to make him so little, and yet it's hard. There we go. I is the little horizontal dude, and J is the little vertical dude. I's and J's both have magnitudes of both of them, the unit vectors. If they're unit vectors, they have magnitudes of 1, just like the unit vectors that we saw yesterday. I by himself is the vector 1, 0, which means he goes horizontally, right? Remind me, what form is this? Yeah, component form. I heard some of you trying to get there. Component form is the side carets. Component form is the side carets. So if they both have a length of 1, and if I is 1, 0, what's J going to be? 0, 1. Good. 1, 0, 0, 1. And there's going to be a new type of notation, not just I said it wrong, sorry. Not just nope, I was about to say it wrong again. Component form. Component form, and then there's linear combination. That's the word I kept trying to say, combination form. We haven't seen linear combination yet. Component form is the one with the side carets that we just talked about or reviewed. But let's come back here. If I was to ask you right now how to write this guy, vector V, with this picture, how to write him with I's and J's as vector addition with I's and J's, would that make sense right now as it is? 1I plus 1J is V, yes or no? No. Why not? Because it's not just 1 and 1. If it was 1 and 1, where's the hit? Over here somewhere. I need to go all the way over there. Well, hold on. What am I going to do to the I to get all the way over? And what am I going to do to J to get all the way up? 7 times I plus 5 times J. So right now we can actually, getting closer to this linear combination form, we can actually write a vector in terms of its I and J components. And I probably gave this to you a little bit soon. Let's put this in parentheses. We're going to talk about this notation on the next page. But vector V goes over 7 and up 5. Here's the long story short. Vector V is not a unit vector, right? Why is it not a unit vector? Well, what's his magnitude? Definitely more than 1 over 7 up 5. What is it specifically? Wouldn't I find it by taking the square root of a squared plus b squared? You guys are doing the math. 49, 25. 49 and 25 is 74, right? Square root of 74. But long story short, is it more than 1? So if they are asking, or if they do ever ask us to find a unit vector with the same direction, but it's going to have a different length. If this has right now a length of square root of 74, which can anyone give me like the whole number that's in that quantity? Square root of 74 would be, why is it 8 point something? How do I know that right now, right away? It's between 64 and 81, right? So I can, this has a length of 8 point something. Well, what about a length of 1? What's that going to have? It's way down there. Well, how do I get here? how I find a unit vector of V. A unit vector of V. A unit vector of V is to take the A all over the magnitude and the B all over the magnitude. This page got a little wonky because I accidentally showed you this form early. I apologize for that. Long story short, vector V goes over 7 and up 5. As a result of that, think Pythagorean theorem, his hypotenuse or his magnitude, V's magnitude, is way bigger than 1. We just talked about how he's 8 point something because it's the square root of 49 plus 25. And since his magnitude is not 1, we have to scale him back. And how do you scale things? You multiply or divide. If you want to double or if you want to triple, if you want to cut in half or cut in third, think about like zooming in and zooming out in a sense. If you want to scale it, you have to multiply or divide. This one, don't multiply by a whole number. That's going to get us in. And so if we take the old if you take the old vector V, which had the 7 and had the 5, and say, okay, that's important, that's who you are, but I need to scale you back. What are you going to scale him back by? The square root of 74. Now, did anybody break down 74 and see if there were any perfect squares in there? 2 goes in 37 times. 37 is prime, isn't it? Does anything go into 37? So technically, the unit vector for V in this example would be, now, okay, we can handle this. Did I write this in the simplest form? No. What would you do to write it in the simplest form? If I can't simplify that, rationalize it, multiply top and bottom by square root of 74 over square root of 74, right? Rationalize, multiply by square root of 74 over square root of 74. But that is proper. It's correct. I won't say it's proper. You could make it proper to make it match the back of the book, yeah? Okay, so a little bit messy. I'm going to go ahead, just for sake of if you guys are looking at the notes later, or if you're like, wait, that was a really messy page. Let me rearrange this just a little bit. I got a little too excited with my I's and my J's. I don't know why I worked backwards. Let me go ahead and move all of this into like its proper order. This is what we kind of technically should have done. There we go. So, why I wanted you guys to have your highlighter out is because I didn't have this written in a very nice form. But now we do have a formula technically for or given any vector V with components A and B. So a unit vector of vector V given components A and B. You could check with Pythagorean, you could check the magnitude, and if the magnitude is not 1, it is not a unit vector, and so we have to say, fine, I'll take your A, I'll take your B. I have to make you go in the same direction that you're currently going, because a unit vector of a current vector must go in the same direction. Take the A, take the B, but scale back, and scale back with the magnitude, okay? Scale back with the magnitude. Now let's go ahead and go talk about that linear combination form. Here we go. But most of you might be able to go right now and write the linear combination form. The difference between the two, we have the old school component form, and both of these break it down. Both of these in many ways are easier, oh dear, are easier, it's a struggle of a day, are easier than given magnitude and direction, even though Despicable Me chose to use that one. Right? Magnitude and direction, those are actually the hardest to deal with when dealing with vector diagrams. You have all these angles and all these lengths, and you don't have any horizontal or vertical components. You don't have it broken down at all. And so if I was to put that big old picture on the board again and have all these different vectors in play and we have to put them all together to figure out the net, we don't want to deal with all their angles and all their lengths. That's so hard. Even though it's kind of fun. We want to deal with the horizontal and vertical components. So one way of writing it is the way that we've already talked about with the side carets. The other way is going to be using a linear combination, aka a vector addition, using the unit vectors I and j. So the nice thing is, you plug in the exact same numbers either way, you just plug it in different ways. So guys, what's the component form? All I'm going to plug in is 4, negative 5. So you could think you always just plug in, right? Going a positive 4, going a negative 5. This one just gives me, but it typically is from an initial point to a terminal point, or I should say it's always from the initial to the terminal, so you will end up at the right end of the vector as long as you start in the right spot. Linear combination is the exact same thing, except technically what it does when you put in the 4 and the negative 5, it puts little arrows on it and says, hey, it's not just lengths, it's actual vectors that add together. So when we do components, technically I was never writing arrows because you weren't really doing vectors. You were just doing lengths. But with the i's and j's, we're technically doing actual vectors. 4 over and 5 down. Basic operations work the same way. So what do you do? 2 times vector v. Uh-oh, pause. Are you putting little arrows? Love everybody, everybody. Vector u gets 1. Vector I gets 1. Vector j gets 1. Vector v gets 1. I gets 1. J gets 1. 2 vector v. Vector v. Vector u. Sorry, vector u. Vector v. What do you guys think doubling vector v is going to end up doing to the linear combination? And changing which pieces? Both, right? So what is 2v going to equal? Two times 3 and 2 times 2. It's as easy as that. Right? How about u plus v? What's that going to equal? 4i plus 3j. 4i plus 3j. So far, easy cheesy, true? And this is why you guys don't like unit vectors, because in the midst of easy, you're like, oh, I have to think. You're welcome. What do you guys think? Unit vector of u. Which is a little weird. It's going to be the unit vector of u, but that's all right. Try to apply what we just talked about with i's and j's instead. What do we still start with? Yeah, let's see if it's a unit vector. Maybe it is. Now, some of you are like, of course it's not. Well, hopefully you know why of course it's not. But real quick, what is the magnitude of vector u as is right now? Square root of? Good. A squared plus b squared. Careful. Make sure you're looking at vector u. So taking the a and taking the b, taking the 1 and taking the 5. That would end up being the square root of 26. So is this a unit vector as is? No. Okay, so how do we make it a unit vector? We ask him, who are you, and who is he? 1i plus 5j. So put the 1, put the 5, but why am I putting division? I have to scale it back. Dividing by the magnitude, square root of 26, I can say, haha, I'm scaling you back. I'm dividing by the magnitude. And when I scale back the hypotenuse, dividing by the magnitude, I'll get 1. And everybody else, well, it's not going to be quite as pretty as 1, but that's okay. I don't need the legs to be 1. I need the hypotenuse to be 1. So there are a few different ways of writing it. One way is you could just rationalize each individual piece, root 26 over 26i. Multiply top and bottom by square root of 26. What would the next piece be? Got it. Some people would take like the 1 over 26 and take it out. I don't think our book specifically does, but just kind of showing you what someone else might do. The i's and the j's are never under the square roots, though. Just be careful of that. You could technically rewrite it like that, and you would be right. It's taking these little... Ew. Okay, that's fine. But either way, you have a unit vector of u by taking what was currently the 1 and the 5 from right up here in the linear combination and dividing by the magnitude we found off to the side. That's probably the preferred answer, I think. I think that's the preferred answer. Ready, Freddies? Ready to go deeper? Let's check out homework really fast. So far, yesterday, and maybe some of you might want to stop me right now if you got stuck somewhere up on this first page to ask me a quick question. Showing that vectors are equal, finding the component forms with the side brackets, the component forms. Wait, which way did you guys subtract on these ones with the points? Terminal minus initial. Good. The x minus the x, the y minus the y. Side carets as well. Ooh. What can we do now? Where some of you might have been able to do this already. Oh, except, did they give us numbers? They gave us a picture. You weren't supposed to do numbers. You weren't supposed to be making up numbers or giving numbers, even though you could kind of do like -2, 1, and maybe like a 1, 2, and a 1, 2, 3, 5, 4. You could maybe make up numbers if it helps, but you were supposed to be doing a picture. So for instance, if you did need to do number 25, what would it look like? How would you graph it? This, but flipped. Good, with the arrow going this way. Or you could actually move it down and have it down there. But yeah, either way, the arrow flips. How about this guy? In a sense, combined. Don't they have to flow through each other? Can they flow through each other right now? So what do we have to do? What did I do yesterday when we had to flow through? I bring it up and then follow the flow. What would the sum be? Yeah, the connection, the net. This one might be a little tricky. What happens if you start multiplying by numbers? What happens to the lengths? Starts doubling or cutting in half or quintupling. Is that the thing? I don't know. But anyway, just a quick little hint on that because I know that page would be a little bit tricky, but we're moving on. What's going on up here? Is this going to be easy? As long as you don't make math mistakes, yep. Jason's group, you're failing him. How about this section? Aiden's group, you guys are doing all right? This group, not this group, sorry, this section. Unit vector, what are you going to be doing? Taking A's, taking B's, and dividing by what's? Magnitudes? Wait, if it comes in component form, what are you going to have the answer be in? Oh, it's meant to be easy. If you get them in components, you're going to hopefully spit it out in components. If you get it in linear combinations, you're going to hopefully spit it out in linear combinations. Wait a minute. What if there's no I, but there's a j?
0.
It's like this one. 3i plus 0j. We wouldn't write the 0. It just goes away. So same thing down here. You can make it 0i plus 4j or negative 6i plus 0j. What's going on down here? I think we need some more to learn. Okay, so let's come back to our notes. Did anybody read the directions fast enough and are still remembering what it said? What was the next section in homework? Something about direction and magnitude, I think. Oh, hey, despicable me. Now it's time to talk about it. Something like that. Direction and magnitude. Direction and magnitude. Direction angles, the angle formed with the vector and the horizontal. Here's a dealio, and those complicated deal with the information, but that doesn't mean that you're never given that information. Very rarely, if you're doing navigation, would someone say, hey, go over this much and up this much and use Pythagorean to figure out where you're actually headed. Yeah, that's not very practical. They're going to say, oh, turn to this bearing and go out this distance. That'd be a lot easier. And so since it's more practical as far as like navigation or as far as actually traveling where you need to go, not analyzing a situation, we have to talk about what do we do in direction and magnitude, or if we're not, but we want it. Kyle, what's up, bud?
Is V1 and V2 bolded or not?
No. No. In your book, it's going to use V1, comma V2, and I like using A and B. Does that make sense? So when I'm this up above, what I'm saying is that they gave you some sort of vector V, whether it's with I's and J's, whether it's with component form, but they've given you like a V1 and a V2. So I'm letting you guys see the book like this. I say A and B. Yay. I just like it better. I like A's and B's better. So this is a really, really, really crucial page. If you guys are highlighting kind of people, this is a page to be highlighting. But let's get the formulas first so you know what to highlight, okay? Because this one says they might give you theta, they might give you magnitude, they might be like Despicable Me, and you're like, I don't want that. I want the A's and B's because they're easy to add and subtract and multiply and divide by constants and not by vectors. We don't know how to do that yet. So Despicable Me gives you magnitude and direction. You're like, ew, gross. What do? Well, you say, hey, it's just the right triangle. You say, hey, it's just a right triangle. I can deal with triangles. If they give you theta and magnitude, so given magnitude and direction, that might be a good little note to give yourselves off to the side. Somehow you're given or you can find the magnitude and the direction. And you need to do some sort of math to the vectors. You need to somehow analyze, put it all together. This is what you need to use. What trig function can put together theta and magnitude in A? What's going to help me relate these three? Cosine. So I can say cosine of theta is equal to adjacent over hypotenuse. A cosine relates magnitude, direction, and A. I like A. I like this, or I like that. I like components and linear combinations. The math is easy. But here's the dealio. We're not going to know A. We're going to need to be finding A. So a quick rearrangement would let me get the formula that I can actually use just by multiplying. Magnitude. Cosine theta is equal to A. Look at your triangle. What relates theta and magnitude, direction and magnitude, and B? Sine. With one quick little rearrangement, I can say, hey, give me the magnitude, give me the direction. I don't mind, I'll get my B myself. Because B is just going to equal magnitude, sine angle. However, there are times, and I think this is where homework is going next, where you are given your components or you are given your linear combination and they need to know the angle. Let's say they're like, well, great, that's great on paper, but I'm here, I'm steering, I need to know what angle to turn. Tell me what angle. Well, how do you do that? Big deal. What relates theta with A and B? So we need the angle. We are going to use, some of this is ringing a bell. It should be. Just maybe we didn't have all that vector notation back when we first talked about it. Why am I going to use tangent inverse of B over A? If I plug that in my calculator, how many answers do I get? But if you're like, couldn't you turn 360 degrees? That's a lot more than the one possible answer. There might be 2 or 3 or 4 different possible. Which one is the right one? You use this in the context of the problem to figure out what angle to give. Now my highlighting tables. Now it's time to go ahead and highlight each of these important formulas. If they're playing a Despicable Me on you, giving you magnitude and direction, you're like, ugh. Or at least when I do an example the long way, you'll be like, ugh. But using those formulas, give me an A, give me a B. I like that math. That was easy. Adding U and adding V, multiplying U times 2. I like that step. If it's written these ways, you can get your A, you can get your B. But what if you're here with your paper and you're playing B's, and then someone's like, I need the practical application. Give me theta. Fine, there's theta. Wait, what if they say, I need the practical application. I need where to go. How would you find magnitude? Yeah. So if you want all the formulas in one place, you could go ahead and do it here, because the magnitude, even though we've already talked about it, you've already talked about, hey, if I have my A and my B, Pythagorean can get me my magnitude. So where on earth are we going with all of this analysis stuff and all of this? How do you add? How do you subtract? How do you multiply by 2? How do you go from angles, directions, and magnitudes to A's and B's? Well, here's a great example. Oops, it's a little bit messy too. Lo siento, I don't know why. Do you guys see how they're playing a Despicable Me on you? What have they given you for U and V? A magnitude for each and a direction for each. Didn't we talk about yesterday how, if you have two different guys, 50, 30 degrees, wouldn't that be this guy? How do you add these two? When they say magnitude of the resultant, direction and magnitude of the resultant force, it'd be the net, it'd be the combined, it'd be the U plus V. How do we add vectors? Don't we have to move this guy? So I'm going to go ahead and move this guy and say, I don't want you here, I want you here. If we were doing this geometry way, we would have to say, okay, cool. I want this, and I want, in a sense, this. I want the angle. That's what they're asking for. Okay, geometry. This is 30, and this is 110. This would be what? We have to use a little, like, angle addition. Couldn't we do minus 30 to get 80? And then we could go ahead and say, oh, and this one is 30, and this one is 50. Oh, could we S law of sine and figure out which case is the right case, and figure out the other sides and the other angles, and then figure out what's going on? See you guys later. A's and B's easier. Toodles. Yeah, we're picking up with this one. I'm going to finish the geometry and then be like, was that fun? No, let's just do A's and B's. And how much easier is that? Does that make sense? I'm still playing around a little bit.